Victorian English visitors to the Outer Hebrides wrote home about primitive squalor. Stone huts filled with smoke, no chimneys, families sleeping in the same room as cattle. The kind of backward living you'd expect from people who hadn't figured out basic architecture yet. Except the Scottish blackhouse wasn't primitive. It was a precision-engineered survival system designed for one of the most hostile environments in the British Isles. A place where 90 miles per hour hurricanes rolled straight off the Atlantic with nothing to stop them. Where 80% humidity made freezing temperatures feel like they were carving into your bones. Where there were no trees for timber or fuel, and winter lasted 6 months. The blackhouse solved all of it. With walls that doubled as fertilizer factories, a chimneyless design that retained 50% more heat than proper houses, and a roof held down not with nails, but with hanging stones that let the whole structure flex during force 10 storms without tearing apart. This wasn't a house people eventually improved. It was an integrated survival machine where every element, the smoke, the stone weights, the 2-meter-thick walls packed with peat, served multiple functions simultaneously. Shelter, yes, but also industrial smokehouse, textile factory, livestock barn, and closed-loop fertilizer production system. 6 engineering solutions, developed over centuries, that kept Scots alive in conditions that would have killed anyone relying on conventional architecture. The Outer Hebrides sit in the North Atlantic, with precisely nothing between them and North America. No mountain ranges to break up weather systems. No landmass to weaken storms. Just 2,000 miles of open ocean, what meteorologists call fetch, that lets wind and waves build enormous power before slamming into these islands at full force. Winter storms regularly hit force 10 on the Beaufort scale. That's sustained winds of 55 to 63 miles per hour, with gusts exceeding 90. Not once a decade catastrophes, regular weather. And it wasn't even the wind that made survival hardest. It was the humidity. The Hebrides experienced what's called wet cold, temperatures hovering right around freezing, combined with 80 to 90% humidity and constant rain. This type of cold penetrates differently than continental winter. Dry cold at minus 10 degrees Celsius feels harsh, but manageable with enough layers. Wet cold at 0 degrees Celsius with 85% humidity pulls heat straight out of your body. The moisture conducts warmth away from skin faster than dry air ever could. Physiologically, a wet 0 degrees Celsius day feels like minus 10 degrees Celsius in dry conditions, which meant traditional insulation didn't work. Wool gets heavy and loses its insulating air pockets when damp. Fabric stays wet for days. Your body constantly fights to maintain core temperature, while the air around you actively steals heat. Then there was the treelessness problem. Centuries of deforestation combined with naturally boggy, wind-blasted terrain meant virtually no trees grew on the islands. The resource that every other European culture used for building frames, roof beams, furniture, and fuel, gone. Not scarce. Essentially non-existent. So Hebridean Scots couldn't just adapt typical designs. They had to engineer backwards from survival requirements and invent solutions using only stone, peat from bogs, and whatever grass grew in that hostile soil. Most architecture starts with available materials and builds what's possible. The blackhouse started with what will keep humans alive through 6 months of wet hurricanes, and worked backward to create the materials that could do it. The core technology was the wall itself, not one wall, 2. Running parallel with a gap between them. Blackhouses used what's called double-skin construction. An outer wall took the direct punishment from wind and rain. An inner wall provided structural integrity and held the heat. The space between them, 60 to 90 centimeters, roughly 2 to 3 feet, wasn't left empty. It was deliberately packed with insulation, peat specifically, also dried moss, earth, sometimes straw or heather. This created a composite system where each material contributed different properties. Peat, when dry, insulates similarly to modern fiberglass in terms of R value. The moss absorbed moisture. The earth added mass. Together, they formed a barrier that could breathe, pulling humidity from the interior while blocking exterior water, without letting cold penetrate. Here's why that mattered. Stone alone is a terrible insulator. It conducts heat poorly, which is why stone walls feel cold to the touch. But thick stone acts as thermal mass. It absorbs heat slowly and releases it slowly. The problem is that if your interior heat ever reaches the cold outer surface, it escapes into the Atlantic wind, and you've wasted fuel keeping the outside warm. The cavity solved this. Heat from the interior fire warmed the inner stone wall. That heat tried to conduct outward, but hit the peat moss earth barrier, which stopped it. The outer wall stayed cold. The inner wall stayed warm. The buffer zone between them moderated temperature swings and prevented the thermal bleed that kills you in wet cold. Think of it like a thermos bottle, except the vacuum layer is replaced with organic matter that also manages moisture. And then there was the maintenance cycle, which doubled as fertilizer production. Every 3 to 5 years, families removed the cavity fill. By that point, it had compressed and absorbed moisture from years of use, but it had also been enriched, infused with residue from peat smoke, organic decomposition, and the minerals leached from the stone itself. This material got spread on fields, where it improved the thin Hebridean soil that was naturally acidic and nutrient-poor. Then they repacked the cavity with fresh peat and moss, cut from the bog and dried over summer. The walls weren't static architecture. They were a renewable resource system. The house insulated you, then fed your crops. Then you rebuilt the insulation on a 3 to 5 year cycle for generations. The blackhouse wasn't just sheltering people from the Atlantic. It was turning survival infrastructure into agricultural input, using the same stones over and over while the organic matter cycled between walls and fields. Victorian visitors saw the smoke and thought, no chimney meant, don't know how to build one yet. They were wrong. The absence of a chimney was the most deliberate design choice in the entire structure. Blackhouses retained 40 to 50% more heat than comparable buildings with chimneys. In an environment where fuel was scarce and cold was constant, that wasn't a minor efficiency gain. It was the difference between surviving winter and freezing to death in your own home. The physics are straightforward. Hot air rises. In a standard chimney system, that rising heat exits directly through the roof, and you've just burned peat to warm the sky. In a blackhouse, rising heat had to work its way through the entire thatch roof structure first, transferring warmth to the living space below for much longer, before finally dissipating through the permeable thatch and stone gaps. You weren't venting heat. You were forcing it to do extra work on the way out. But heat retention was only the first function. The smoke itself became a preservation technology. The constant low-level smoke throughout the interior created a cold, smoking environment. Temperatures between 20 and 28 degrees Celsius for 12 to 24 hours or longer. Fish, primarily herring, cod, and mackerel, hung from roof beams alongside mutton. The smoke preserved the protein without cooking it. No refrigeration, no ice cellars, just smoke, doing continuously what other cultures had to do in dedicated smokehouses. Peat smoke also contained antibacterial compounds that inhibited spoilage and killed parasites. You were essentially sterilizing your food storage, your bedding, and your living space all at once, passively, as a byproduct of staying warm. Then there was the thatch itself. Roof thatch in a smoke-filled blackhouse could last 15 to 20 years. Thatch without smoke treatment rotted in 5 to 7 years. The smoke waterproofed the straw, prevented insect infestation, and deterred the fungal growth that normally destroyed organic roofing. You weren't damaging your house by filling it with smoke. You were preserving it, and it kept pests out. Smoke drove away insects. Mice avoided it. Rats didn't nest in it. The blackhouse interior was hostile to anything that might eat your food stores or spread disease. The trade-off, obviously, was human lungs. Respiratory issues were common among elderly blackhouse residents. Chronic bronchitis, smoke-damaged airways. But this was a calculated exchange. Potential lung problems in old age versus guaranteed starvation or hypothermia in youth. The smoke wasn't a flaw in the design. It was the design. Heat retention, food preservation, waterproofing, pest control, and structural longevity. All from the same peat fire that you needed anyway to not freeze. What looks like primitive squalor to a Victorian observer was actually 5 survival systems stacked into one architectural feature, running 24 hours a day for 6 months straight. The roof couldn't fight the wind. It had to move with it. Blackhouse roofs used thatch, oat straw, barley straw, or rye, packed densely over a wooden frame. But the frame itself was precious. Often driftwood, sometimes imported timber, reused across generations because trees didn't grow here. Once you had those beams in place, you couldn't afford to replace them every time a storm ripped the roof off. So the thatch wasn't nailed down. It was tied down with a network of ropes. Heather rope, straw rope, later hemp, and weighted with stones. Not stones sitting on the roof. Stones hanging from the ropes, suspended on the exterior, creating a net pattern across the entire surface. This is the opposite of how most people think about securing something. You'd assume the answer to, how do I keep a roof attached during a hurricane, would be attach it harder. More nails, stronger fasteners, rigid connection. But rigid structures in extreme wind create stress points where everything fails at once. A nail holds perfectly until the wind pressure exceeds its shear strength. Then it tears through the material completely. The roof doesn't loosen gradually. It explodes off the building in one catastrophic failure. The blackhouse system built in controlled failure. The weighted ropes allowed the thatch to lift slightly when wind pressure built underneath. Release some of that pressure, then settle back down. Like a pressure relief valve, the roof could flex a few inches, absorb the force, and survive instead of resisting until it broke. Each stone was selected for specific weight. Heavy enough to hold the thatch in normal 40 to 50 miles per hour winds that were just regular weather. Light enough not to tear through the straw during the flex cycle when a force 10 storm hit. This wasn't written down engineering. It was empirical knowledge passed down through families. You learned which stones worked for which sections of which roofs by watching your father adjust them after every storm. Then there was the profile. Blackhouses sat low. Thick walls extended slightly above the roofline, creating a parapet that blocked wind from getting underneath the thatch edge where it could pry upward. The corners were rounded, not square, so wind couldn't slam into flat vertical surfaces. The roof slope was gentle, steep enough to shed rain, shallow enough not to catch wind like a sail. The entire structure hugged the ground, aerodynamic, in the sense that it minimized surface area for wind to push against. You weren't building up. You were building down, making the house as small a target as possible while still being livable inside. And the maintenance was constant. After every major storm, families inspected the roof. Ropes retightened, stones repositioned, damaged thatch patched. This wasn't emergency repair after disaster. It was preventive maintenance built into the rhythm of life. The house was a system that required attention. Like a boat, you had to bail and caulk and check for leaks because the ocean was always trying to sink it. The roof was ship rigging applied to architecture. The same engineering philosophy sailors used to keep masts standing in hurricanes. Tension, flex, controlled gov. Adapted for a building that faced storms just as violent, but couldn't sail away from them. Modern earthquake engineering in Japan uses the same principle. Structures designed to absorb force through movement, rather than resist it through rigidity. The blackhouse figured this out for wind centuries earlier, using rocks on ropes because that's what they had. And it worked. These roofs survived conditions that would have torn conventional buildings apart. Not by being stronger, by being smarter about where to yield. Chapter 5. The blackhouse wasn't just a house. It was a factory, a barn, a smokehouse, and a fertilizer plant operating simultaneously in roughly 60 square meters. Start with Harris Tweed. The Outer Hebrides' primary export, the wool fabric that put these islands on the economic map, was produced inside blackhouses. The looms took up significant floor space, not tucked in a corner, but central to daily life. And the environment itself was part of the manufacturing process. The constant humidity from cooking, breathing, and the permeable stone walls kept wool fibers pliable for spinning and weaving. Dry air makes wool brittle and prone to breaking during processing. The blackhouse maintained exactly the moisture level that made wool workable without rotting it. The smoke naturally treated and slightly dyed the fibers as they were processed. You weren't fighting your environment to produce textiles. You were using it as industrial infrastructure. Then there were the animals. One end of the blackhouse housed livestock during winter. Usually cattle, sometimes sheep. This wasn't quaint mixed-use farming. It was thermal engineering. A single cow generates roughly 1,000 watts of body heat continuously. In a small enclosed space during a 6-month winter, that's significant supplemental heating that costs nothing but the fodder you were storing anyway. The animals also produced manure, collected daily and composted outside. But even the collection process was optimized. The floor in the animal section was often slightly sloped toward the door, so waste could be scraped out efficiently. Nothing was casual about this arrangement. The spatial layout served specific functions. The human living area centered on the peat fire. Cooking happened here. Heat radiated here. This was the social center where stories were told and music played. The Scottish Chalith tradition was born in these smoke-filled spaces. Sleeping areas occupied the opposite end from the animals, far enough to avoid the smell, but close enough that body heat from both livestock and humans mingled in the middle zone. Vertical space was productive too. The roof beams weren't just structure. They were drying racks and smoking racks simultaneously. Hundreds of fish hung there during seasonal processing. Herring runs came in massive waves, and families split, salted, and cold smoked more than they could eat, creating trade goods that lasted months. You were living inside your smokehouse while it operated, which sounds unpleasant until you realize it meant you could monitor the process constantly without dedicating a separate structure or fuel source. Every waste stream fed back into production. Peat ash from the fire was spread on acidic fields to neutralize soil. When the roof thatch was finally replaced after 15 to 20 years, it went on the fields as fertilizer, enriched with decades of smoke residue and organic decomposition. The wall cavity fill, harvested every few years, was already discussed. Animal manure composted for field use. Even urine was collected and used in wool processing to remove lanolin from raw fleece. Human waste was composted separately and aged before field application. Nothing left the system as pure waste. Everything either cycled back into the house as material input or out to the fields as agricultural input. The efficiency wasn't just ecological, it was economic survival. When you live on an island with no trees, poor soil, and 6 months of hostile weather, you can't afford single-purpose spaces or wasted materials. The blackhouse integrated production systems because specialization was a luxury these people couldn't access. Modern industrial thinking separates functions. Factory here, home here, barn here, warehouse here. The blackhouse collapsed all of it into one structure because the energy cost of heating multiple buildings would have been fatal, and the material cost of building them was impossible. What looks like cramped multi-use chaos was actually sophisticated space optimization. Every cubic meter had multiple jobs. The same smoke that heated you also preserved your food and waterproofed your roof. The same walls that sheltered you became fertilizer. The same room where you slept also produced the textiles you'd trade for the things the island couldn't provide. The system worked for centuries. The last permanently inhabited blackhouse was likely occupied into the 1970s. It didn't fail. It was replaced. Victorian authorities and modernization programs deemed it unsanitary and backward, pushing white houses with chimneys, separated animal quarters, and modern amenities that aligned with contemporary standards of hygiene and progress. But in terms of pure survival efficiency for that specific environment, the blackhouse was close to optimal. Its replacement wasn't necessarily a functional upgrade. It was a cultural shift towards standardization, comfort, and values beyond mere survival. The blackhouse disappeared, not because it couldn't keep people alive, but because staying alive wasn't the only measure of success anymore.